Hello everyone, my name is Yuxuan from Nanjing University, China. Today, Cheng, Gong, Evgeny and me are going to present our paper, Keyword Search over Knowledge Graphs while Static and Dynamic Have Labelings. Different from Sparkle queries, Knowledge Graph query can query web data without prior knowledge of specialized keyword query languages. For example, you can type in 8 researchers' names and find the connections between them on DBLP. For example, Jennifer Whedon had a paper cited by a paper written by Han Jiawei and Pei Jian. The paper also cited a paper written by Phillips Yu. Jennifer Whedon has a co-author who has a co-author, Michelle Jordan. The challenges for this problem is that the problem itself is MP hard, and nowadays knowledge graphs are huge. For example, DBpedia and Google Knowledge Graph contain millions or billions nodes. According to the recent survey, existing methods don't scale. They usually take thousands of seconds to answer one single query for knowledge graphs like IMDb. Now we formulate our problems. In knowledge graph, vertices denote entities. Undirected edges denote relations between entities. We assume there is a weighting function mapping edges to non-negative real numbers 0.4, 0.1, 0.3. On the right side is the knowledge graph. You can see vertices and edges are denoted by symbols, but in real knowledge graphs, they should be meaningful text. A keyword query is just a list of keywords. Keyword mapping is a retrieval function that maps keywords to a keyword node set. B is mapped to K1 is mapped to B, and K2 is mapped to E. K3 is mapped to C and D. For each keyword, we have a set of keywords that can be mapped from. C is associated with K3 and K4. B is associated with K1. Our goal is to find the minimal age-weighted tree that can contain all the keywords. You can see the orange subtree. That is our goal. It contains K1 in B, K2 in E, K3 in C, and the sum weight is 1.3. We don't consider directed graphs as our algorithm can be easily extended to directed graph. We don't consider the exact weighting function and retrieval function, as it's not our concern. We don't consider a retrieval function to map to edges because we can handle it easily. Now let's look overview our algorithm. The algorithm consists of 3 steps. The first step, we enumerate all the nodes in K1, B, and F. Then for each node, we find the nearest vertices in each keyword set. So for B, we want to find the nearest neighbor in K2 and K3. F is the same. And the weight of this set is BE plus BC. BE plus BC is 1.8. The weight of this set is FE plus FC is 2. And so UB has smaller weight. This is our goal. And we want to preserve the set to the second step. In the second step, we enumerate all the vertices in the set and repeatedly choose the unchosen vertices in the set and add the shortest passes between the temporal answer tree to this node. For example, we choose B, then there are two candidates, C and E. We choose the shorter one, is BE, added to the answer tree. Then we have temporal answer tree BE, and add the shortest path between C and the answer tree CAE. Then the second we choose E, and the shortest path is EAC, then we choose AB. The third is choose C, the shortest path is CAE and AB. The third step is we choose the smallest tree we found in the second step, and the answer tree, it is done. You can see in the first step, we need to find the shortest path distance to get BEC. In the second step, we need to repeatedly find the shortest path between node in the temporal answer tree and the node outside the unchosen set. And how can we efficiently solve this? We use hub labeling to achieve this. What is hub labeling? Hub labeling is just for each vertex S, it has a labeling set. A label is the vertex T and the shortest distance between S and T. In order to get the shortest distance, get D between U and V, we can find the intersection of the label sets. This is the intersection of label sets. They have shell vertex H, and because the label we have the distance between U and H and the distance between V and H, we choose the minimal distance, and this is the answer. As long as the label preserves this formula, we can say this is the hub label. If we sort the labels according to H, then we can use, in advance, we can use a merge sort join to align, efficiently join the intersect the label sets. So for online query, the running time is linear to average label size. Let's see an example. For each vertex, we have a label set. It's a node, and the distance between A and the node. You can see the distance between C and A is 0.4. And we sort it according to A, B, C, D, E. It has A, B, E. Now let's see how to calculate get D, E, F. We use merge sort join to get the intersection is A and B. The corresponding distance is 0.3 plus 0.7 is 1. 0.8 plus 0.1 is 0.9. So the minimal this answer is 0.9. You can see EF, we go through B and distance 0.9. It's true. As we mentioned above, if we sort it in advance and perform merge sort joins, the running time is linear to the average label size. There are already some heuristics to minimize the average label size. For example, degree ordered based PLL, business order RXL, and significant path order SHP. We propose business centrality order SHL. It chooses vertices through which many shortest paths is passed. And the idea is similar to betweenness order. The difference is that RxL assume each pair of vertices have the same importance. But we think if a pair of vertices is passed by many vertices, it shouldn't be that important. And we find the betweenness centrality satisfies this condition. So we want to use betweenness centrality. Unfortunately, the well-known algorithm, Brand's algorithm, to calculate the betweenness centrality runs in n squared log n. So we select the highest degree vertex as pivot to approximately calculate the betweenness centrality. Now we consider how to calculate the distance between u and v. Shortest path. First of all, we calculate the distance between u and v and get the medium node. The knowing method is to record the processor of shortest path between h and u and during the construction. And we recursively call get distance between h and the processor of h and u to get the shortest path between h and v. We recursively call get distance h and the processor of h and v. Our improvement is that we find that during the construction of hub label, if we find h, then h must lie in the shortest path from h to u and h to v. It means for any node in the shortest path, h must in its corresponding label set. So after we find h, we can recursively perform binary search to find h rather than call get distance. Let's see an example. The difference is that now we have a processor during the construction, and we try to get the distance between D and F as shortest path. First of all, is a get distance D and F. We perform merge sort join, and the common vertex is A. So H equals A. Then we will find the shortest path between A and D and A and F. We find that the processor of D is A, so the shortest path between A and D is just A and D. The shortest, the processor of F is B. Then we perform binary search in LB to find A. The processor is A, so the shortest path between F and A is B, FBA. We merge it to DABF. DABF. This is the shortest path. This is our algorithm KKG. We can prove that its approximation ratio is G. G is the number of K-words. The running time is roughly n cubed times G plus n squared times G squared. And actually its running time is L times n squared times G. L is the average label size and is bounded by the number of nodes n. So it's n cubed G. But in practice, L is very small. Otherwise, we can't even store the labels in memory. So the runtime is not that bad, but it's still not pleasant. The dominating part is that we have to call get distance n squared G times. So do we really need so many get distance? Let's see, what did we do in KKG? In the first, we enumerate all the vertices V1 in K1. Then for each K-word vertex set, we find the shortest distance between V1 and all the vertices in Ki. So n times g times n is n squared g. We avoid so many get distances via dynamic hub label. Basically, it's just a hub label of a K-word vertex set. Rather, further, we hash the dynamic hub label. So when we call get distance, we need just a hash join. And because it's a hash table, we can't have the same vertices with different lengths. We can directly preserve the smallest distance. Let's see how we construct it. For K2, it only has a vertex E, so we scan all the labels in LE and hash A to the location of A with the shortest, closest vertices and the corresponding distance 0.3. For B, we hash it to B and the distance 0.8. Hash E to and the distance is 0. Let's see how we construct the dynamic hub label for K3. K3 contains two vertices C and D. We scan all the labels in LC in the location of A. The closest vertex is now C and the distance is 0.4. And to say 0, LD, we hash it to A. It already have a vertex with smaller distances, so we just through it. Again, we hash D to the location of D with 0. Now let's see how we modify get distance. Because K3 now is a hash table, we need to hash the labels of B to get the corresponding distance. For example, the distance between A and the K3, we hash A to the location of A, and the distance is 0.4 plus 0.6, it's 1. And we hash B to the location is none. So the only option is went through vertex A and the corresponding pair is B and C. Now we know the shortest node pair is B and C. We can directly use get the shortest path to retrieve the shortest path. In contrast, if we don't use dynamic hub label, we need to firstly get distance between B and C and the distance B and D. You can see the label of B is scanned twice. Now we only scan it once. This is our algorithm KKG plus. Its approximation ratio is also G, but its running time is faster. Now it's n squared G plus ng cubed. And actually its running time is L times n times G. L is really small, G is really small, so it's rather fast. And the main difference is that get distance is only called n times G times, and get distance is faster because we don't need to scan the two label sets, only one label set. Now look at our experiment. We have three data sets. Mondia is a small geography knowledge graph. Linked MDB is a medium-sized movie knowledge graph. And DBpedia. For keyword queries, we collect some real-world queries. The keyword mapping function, we just use keyword label, RDF label, and build inverted indexes. For the age weight, we choose random real numbers. You can find all the data, keyword queries, and the running results in the paper. We have two baseline. PRDP is the state-of-the-art exact algorithm based on A-star search, and we have Banks 2. It's a state-of-the-art approximation algorithm based on bi-directional search. When comparing the running time, you can see our KKG plus is much faster, at least 3 orders of magnitude faster than the baseline. And the sacrifice is that our approximation ratio is worse, but it's still acceptable. It's only 1.3 in the worst average case. Then we consider the average label size and its running time. PLL, XL, SHP, we have mentioned it's we have SHL with 3 variants, with 10 pivot, with 100 pivot, with 200 pivot. We decide to use 100 pivot. It has smaller label size, and compared to SHL with 200 pivots, it has even smaller average label size, but its building time is unacceptable. Our SHL have comparable running time with IXL. So the conclusion is that KKG plus is much faster with slightly worse result compared to the baseline. You can see the running time. Even our disk-based version is much faster. And we compare KKG with our SHL and the KKG with PLL, which it tells us smaller label size helps. And when it comes to the virtual work, in this work, we only consider top 1 results, while we also generated some other trees in the process, but they don't have any guarantees. In regards to the approximation ratio, we will try to deal with top K in the virtual work. And for dense graph, hub labeling hardly works. Our KKG plus also hardly works. And for dynamic graph, hub labeling just don't work. So it's still an open problem. And thank you for your time.